3,500 years ago, something fell from the sky every morning for the Israelite camp and vanished by noon. For millennia, scholars called it miracle or myth, until a cluster of modern studies and field samples forced us to ask again what the Hebrews actually knew about the origin of that substance called manna. In 2023, a multidisciplinary team led by Dr. Miriam Al Hassan at the University of Negev published a set of samples that changed the conversation. What did they really collect on those flat trays of memory and scripture? What chemical signature would prove a natural process rather than a supernatural act? And how do four competing explanations stack up against the material record and centuries of oral description? We will follow the evidence step by step and try to answer what the people of the Exodus may have understood about the world that produced those flakes. The traditional account is vivid and specific. The narrative in the Pentateuch describes a white thing like coriander seed, tasting like wafers made with honey, that appears as dew on the ground before dawn and disappears under the sun. Imagine the sight of a pale film across campgrounds, the soft crunch between teeth, the sudden sweetness, and the questions that would follow every morning. We hear the report as a sensory reconstruction: sight, touch, taste, even a faint smell of sweetness and of earth. In ancient commentaries, travelers compare it to angel food and to resin. For generations, rabbis and Bedouin storytellers alike offered practical notes that it could be collected with nets or scraped from rocks, and the children ate it without ill effect. But science treated the story as theology or metaphor until teams in the last decade treated those texts as ethnographic clues and went into the field. Excavators looked for stratigraphic signatures that could match repeated shallow deposits rather than a single catastrophic layer. They asked chemists to test for sugars, polysaccharides, trace salts, and microscopic biomarkers. They asked geologists whether faulting or salt domes could produce white efflorescences that mimic food. The search began in 2018 at a low terrace east of the Wadi El Arup, where pastoral traditions still mention a morning crust. Dr. Luis Ortega directed the first season with field archaeologist Ahmed Rahim and cultural historian Sarah Kaplan. On the second morning of work, Ahmed called out from a shallow scrape. "Come see this white film," he said. Miriam crouched past the smear and ran a fingertip across the deposit. "It flakes like powdered sugar," she said. Sarah smelled the sample and frowned. "There is a slight honey sweetness, but also a mineral salt edge." Tomas Nader, the stratigrapher, added, "The layer sits above a camp hearth level, but below a wind-blown sand lens." Elena Petrova, the microarchaeologist, murmured, "Collect everything we can for SEM and carbohydrate analysis." Those short exchanges show how quickly a hypothesis turns tactile. The team collected bulk samples labeled with GPS coordinates and brought them to the University of Negev lab, where Prof. Jacob Weissman, the organic chemist, ran a battery of tests. In the clean lab, a conversation unfolded that would echo in published pages. "The preliminary chromatography shows simple sugars and polysaccharides," Jacob said. "We also see elevated nitrate and potassium," Elena responded. "Hold on," Dr. Lewis said. "There are microfossils in the residue too small to be plant pollen." Sarah leaned closer. "Could those be insect secretions or microbial cysts?" Ahmed asked. "Or a salt efflorescence that trapped organic detritus," Miriam answered. The back and forth continued until the scanning electron microscope revealed tiny spheres and filamentous networks, and the mass spectrometer returned a complex spectrum of sugars, amino acids, and a dominance of sodium and chloride. Sensory notes persisted even in the lab: the faint sweet aroma, the gritty mouthfeel when a technician tasted a minute trace to confirm sensory memory. The physical anomalies were striking and required technical terms. Samples contained microspheres resembling microtectites but at a different composition, mostly silicate glass with a significant sodium chloride component. There were localized zones of melted resin like bitumen on pottery sherds and ceramic fragments with vitrified gloss suggesting brief surface heating. Quartz grains show signs of planar deformation in isolated pockets, while other grains remained unaltered, a pattern inconsistent with uniform high-energy impact. Carbonaceous residues revealed polysaccharide chains similar to cyanobacteriomats and to certain lichen exudates. Radiocarbon dating of associated charcoal placed human occupation levels in the late 2nd millennium BCE, and stable isotope analysis showed elevated 15 values consistent with marine influence or evaporitic cycling. Experts consulted included Dr. Elena Petrova on microstructure, Dr. Miriam on ethnobotany, Prof. Jacob on organic chemistry, and geologist Tomas on stratigraphy and faults. Their names and actions appear through the evidence because archaeology is a conversation between people and soil. From the material record, 4 theories rose to prominence. Theory 1 proposes that seismic disturbance of a salt-rich terrace released saline crusts and gases that produced a white precipitate which mixed with organic detritus to form edible flakes. The mechanism begins with an earthquake along a nearby fault that agitates subterranean brines, bringing saline aerosols to the surface. When cooled at night, sodium salts crystallize as an efflorescence that can trap pollen, microbes, and exudates from plants. This hypothesis accounts for high salinity, nitrate enrichments, and for the recurring seasonal nature, if seismic activity coincided with autumn condensation. Yet the explanation struggles to explain descriptions of sweetness, the wafer-like texture, and the presence of microspheres that suggest melting. Theory 2 argues for a biological origin, an exudate produced by insect activity, lichen, cyanobacteria, or a combination. Examples exist today where scale insects produce honeydew, a sugary secretion that coats leaves and falls into nets as edible flakes for local populations. A well-known modern parallel is the sugar bag honey of certain aboriginal groups, which arises from bee-processed honey, but insect secretions also feed human populations in marginal landscapes. In this scenario, the sweet taste is direct, and the polysaccharide signatures fit. Critics point out, however, that insect yields are typically localized and not reported as widespread morning deposits across campgrounds, and they rarely include vitrified glass-like spherules. At about this point in our narrative, we pause to ask you a simple question. Which theory seems most plausible to you? The seismic salt aerosol, the insect and lichen exudate, or an extraterrestrial event? Type A for salt, Type B for biological, Type C for impact, and leave a brief reason in the comments. Your answers will help us shape future field tests and debate with the team. We read every thoughtful comment and incorporate community observations in follow-up seasons. Now we return to the technical thread. Theory 3 is an impact event, a cosmic airburster similar to Tunguska that heats and lofts surface material, producing microspheres and shocked quartz, while also vaporizing organic films that then recondense as sweet, aromatic carbonaceous flakes. The analogy with Tunguska fits the microspheres and localized vitrification, and would explain reports of a brief bright light and sudden disappearance of the deposit under heat. A 2019 laboratory simulation at the Institute for Planetary Materials produced glassy spherules when peat and halite-rich sediments were subjected to rapid heating and shock pressures. That experiment mirrors some of the Negev lab findings, but not all. Impact scenarios require an energy pulse high enough to melt silicates, yet localized enough to spare surrounding archaeological layers, a uniform destruction which the stratigraphy does not always show. 2 teams published conflicting papers in 2021 and 2022, one asserting impact signatures and the other pointing to post-depositional contamination and modern industrial particulates. In mid-2022, an editorial retraction highlighted methodological lapses in sample chain of custody, and peer reviewers called for repeat sampling and blind testing. The debate is ongoing and healthy. Other explanations and a convergence scenario remain on the table. Theory 4 explores marine aerosols and algal foam. The site sits within 35 kilometers of an ancient salt lake, and paleo shorelines show episodic flooding and evaporation. When saline algal mats desiccate, they can produce flaky biomass that tastes sweet due to concentrated polysaccharides and aromatic compounds. Combine this with localized heating from a volcanic vent or slow bitumen seeps, and you produce caramelized sugars and partial vitrification. Another possibility is a compound event, a small airburst that lofts coastal aerosols into the interior, where they mix with insect honeydew and salt efflorescences, producing a layered deposit that matches the mixed chemical signature we see. To illustrate, imagine the morning air heavy with brine spray, the taste of metallic salt on the tongue, the sound of gulls or distant thunder, a faint warm breath against your skin as a brief flash of light leaves a thin glassy crust on scattered pebbles. Vision, smell, taste, touch, and hearing all converge in that layered reconstruction. Which elements match the ancient descriptions? Wheat-like flakes, sweet wafers, dew. On the ground and disappearance under the sun. The convergent hypothesis tries to fit them all by allowing multiple processes to act together episodically. The consequences are not merely academic. The site at Wadi El Arub shows elevated salinity in soil profiles, a shift in vegetation pollen, and a decline in palatable grasses in levels immediately above the deposits. If periodic salty flakes fell on grazing grounds, that would alter pasture quality and force social mobility patterns that could reflect episodes of migration in textual memories. Today, the trench is a fragile patch of white crust and compacted pottery. The local Bedouin guide Ahmed Rahim points out older terraces with faint white stains and cautions against heavy sampling. The research team has published preliminary protocols with the University of Negev and the Max Planck Institute for the Science of Human History, and set a plan for controlled resampling. 1 month later, the first follow-up campaign expands the sampling grid and applies blind controls. Dr. Miriam Al Hassan reports in a short field note that repeat samples reproduce the polysaccharide signature, and the microspheres persist in 3 independent labs. The team names additional collaborators, including Dr. Elena Petrova at the SEM facility and Prof. Jacob Weissman at the mass spectrometry lab. Local shepherds, led by Ahmed, demonstrate a traditional method of collecting morning crusts with woven mats, which yields microscopic plant detritus consistent with an insect exudate component. The 1-month update also initiates environmental monitoring for soil salinity and nitrogen flux, and records a minor but measurable increase in nitrate at surface layers adjacent to the old deposit. 3 months on, the debate enters peer review and public scrutiny. A replication study by a team led by Dr. Luis Ortega using blind samples finds lower concentrations of glassy microspheres but confirms sodium chloride-rich particles and complex organics. The discrepancy triggers a formal round-robin test where identical aliquots are sent to 5 laboratories, including the University of Negev, the Institute for Planetary Materials, the Max Planck facility, a university lab in Cairo, and an independent lab in Athens. Results published in a collaborative letter show consensus on sugars and salts, but divergence on the abundance of impact-related microstructures. Cultural anthropologists, led by Sarah Kaplan, publish ethnographic notes that widen the comparative context to other pastoral groups who collect seasonal crusts, and recommend including traditional knowledge in interpretation. 6 months after the first publication, the picture becomes more nuanced and institutional. A pooled dataset clarifies that the most likely scenario is a mosaic process in which saline aerosols, insect and microbial exudates, and episodic heating events combine to produce a morning crust recorded by the ancestral memory as manna. Funding agencies, the University of Negev, the Max Planck Institute, and a consortium of Middle Eastern universities commit to a 3-year program to monitor modern analogs and to test preservation pathways. Local communities receive protocols for safe sampling and environmental stewardship, and artists in nearby towns begin to display installations that explore the link between food memory and landscape. In short, the research moves from claim and counterclaim to collaborative long-term science. What we can say now with measured confidence is that none of the simple, single-cause models fully accounts for all empirical traces, and that the Hebrew's description likely encoded a real recurrent phenomenon observed across seasons by people who had sensory categories we can partially reconstruct. Material evidence points to a layered deposit rich in salts, sugars, and small glassy spherules produced by intersecting geophysical, biological, and perhaps small-scale thermal events. That interpretation honors both text and soil and restores the ancient witnesses as careful observers rather than naive recipients of miracles. If you want to follow the unfolding work and see detailed data sheets, maps, and imagery, subscribe to our next installment where we will examine modern analog collection protocols and the full laboratory dataset. For now, keep the question alive in the comments. Type A, B, or C and include a short reason, and we will bring those ideas back to the field team in the next season.